Oh, no, you're all good. I have it recorded, so you're good to keep it once you have it. What was that? I have your exam ones. They're at my office. They were graded by the Scantron and they didn't mark anything right or wrong, but I have the file that tells me which ones you got right or wrong. So if you're curious, come to my office and we'll look through that. Okay, yeah. If you took it out of the testing center, I haven't picked it up yet.
Okay.
So I'll have it later today. If you want to pick it up, you can come to my office anytime.
Okay. Thank you.
Yep.
We can post the grades today too.
Yeah. Grades will be posted today. All right, well, I thought we might just like talk about some of the stuff on the exam. Just for housekeeping stuff, if you are missing anything on Canvas, everything that I'm still missing some submissions for, I'm gonna open back up until midnight on Friday. You have this week to do it. After that, it's a zero. So don't email me asking about it because I have to get grades in very, very soon after Friday. So help me help you. So get your stuff in if you haven't finished it. So that everything should be open now and it'll close on Friday at midnight and we should be good. So overall, much better improvement from the first exam. Some people improve their average score by 10, 15, even 20%. So that's great. It's very good to see. So whatever you're doing, it's working. Keep it up and do that this week because you got an exam on Friday. So finish strong. A couple of questions that seem to catch a bunch of people. Probably the magma properties, that table that you had to fill out. So that caught a few of you. Keep in mind, like magma types, you have your basaltic and mafic, your intermediate, and your rhyolitic. And temperatures range from 10 to 1200 at the basaltic range, all the way down to 600 to 800 in the rhyolitic range. Based on their silica content, they'll have different viscosity. So basaltic, really fluid, not very viscous. Felsic, lots of silicon, very viscous stuff. Another one, the lava butte. This one, that picture one where you saw that rock with all the vesicles in it, that was the key for that question. So half of it was All of those vesicles should indicate high gas content. Need a lot of gas content to create all those bubbles in there, right? The second thing is the location. A lot of this is geographically based. So since this is in Oregon, are we going to be dealing with basaltic magma on a continent? No, we're not. We're going to be dealing with andesitic stuff. So the answer there was andesitic with high gas content. This one was more of just a can you read a map exercise. So make sure you can read a map. All of those red imagery on that map, those aren't lava flows, those are risks for lahars. So make sure you're always reading the legend clearly and making sure you understand your mapping. This aerial photograph taken from the airplane, that's a caldera, everybody. Key was it's a circle. It's a big ass crater. So that's what a caldera is. Most of you did pretty well on the watershed stuff. The word equation, number 34. So the question is the word equation that best describes how much water will reach a channel during a precipitation event. So the key is the water reaching the channel. What water gets into the channel? So the water that gets into the channel is runoff. So what's left to create runoff? Runoff would equal precipitation, that's your whole input, minus your output, your losses from infiltration, interception, and the stuff that evaporates, right? So the key there was the stuff that's flowing into the channel. That's the runoff. 35 was just making sure you were paying attention in lecture, because I talked about the Rodney dormitory building that they demolished and turned into a retention pond. So just to keep you on your toes there. And then the flood stage ones, where it is asking for which of the following velocities best represents the stream at St. Louis when the Mississippi River is at flood stage, 30 feet. So you're given a depth for flood stage, so that's 30 feet. That's one dimension, right? Depth. You're given the width, 1,800 feet. You have two dimensions. Width times depth, that gives you an area, right? So that's feet squared. All the answers here are in feet per second. So the only thing that you have left to use is your discharge, which is measured in cubic feet per second. So if you take that discharge, cubic feet per second, divide it by that area, that cross-sectional area, that'll give you the velocity. So that was a little tough one. Some people got tripped up on it, but a lot of you did the math pretty well. Yep, I think that's it. So overall, great job, guys. Keep it up. One more exam.
Professor Power.
Should be good. Also, if any of you are concerned about your exam grades, just keep in mind, out of a total 500 points for this class, the exams make up 150 of those 500 points. So while doing poorly could like drop you a letter grade, it's not going to make or break you. You have so much stuff on Canvas, all those reading assessments, all the quizzes, all the in-class exercises. Make sure you get those in. That's easy points. So if you're worried about your grade, you're probably doing fine. That being said, don't slack off in the last week, so finish strong. Okay, this week we're going to be talking about soils, subsidence, mass wasting, kind of obscure stuff, stuff we don't really think about when we think of natural hazards. All that too often they get kind of swept under the rug. And in order to understand that, hold on, let me take the chat.
Professor Power.
Levant, you're asking for the answer to that. What's
You know it. You know it. Yes.
You got it right.
My boy. Thank you.
Yeah, the answer there was 9.4 feet per second. So well done. Okay. So to get all of that out of the way, we have to understand soils themselves, what constitutes a soil, how soils work, how they weather, how they erode, stuff like that. There we go. Okay, so the moon used to be a part of the Earth. There was this big ass asteroid that hit the Earth millions and millions of years ago, right when the Earth was forming. And a big chunk of that rocky conglomerate broke off, started orbiting at a certain set distance, and that orbiting thing became the moon. So they're made of the same exact parent material. But all the features on the moon stay the same all the time. All of those, the only thing that has changed the surface of the moon has been the footprints of astronauts past. So why is that? What's going on the moon and what's going on Earth, and why is it different? The key is weathering. We've got stuff going on in our atmosphere that's going to move shit around. If we have winds, we have currents, we have water, ice, all this stuff happening on the surface of the Earth is going to change the way the Earth looks on the surface. This is what I study. This is geomorphology, studying how the Earth's surface changes due to geologic forcings. It's a really cool area of study. But whenever you break it down, what you're really looking at is what are you weathering down into sediment? Are you changing a specific rock to a specific type of sediment? So weathering is the key difference to make here is between weathering versus erosion. Weathering is the physical breaking down of it, the breaking down of the material. Erosion is taking that sediment and moving it. You're moving it elsewhere. You're removing it from where it came from. So we have weathering is the first part, breaks everything down. Erosion moves it away. Keep that in mind as we're working with these differences. Some of you may have seen this feature before. This is Old Man of the Mountain in New Hampshire. It's a national landmark. Well, it was up until 2003. Yeah, quite a few years ago. This is all granite, very hard rock, very, very mechanically hard. Eventually, gravity is going to win, and it's going to collapse off that profile, so we can't see the Old Man of the Mountain anymore. This was first recorded in 1805. It's been a state landmark ever since, but as it was eroding, as it was falling, people tried to fix it and brace it with concrete mending rods. And what they didn't realize is that not only is that not going to stop a geologic force, it's also adding more weight. And if gravity is the driving force here, the more weight you add, the faster that thing is going to fall. So not much they can do now, but at least it lasted long enough to get some color photographs of it. So weathering and erosion doesn't just ruin national landmarks, but it can also cause significant economic and casualties from mass wasting and landslides. So this is in Oso, Washington from 2014. As you can see, this whole side of this cliff face just slumped with gravity over time as the bottom of it was being removed, just slumped right into the stream, basically blocked it off, rerouting the stream into other areas. So this is another way that weathering can impact the surface of the Earth, changes stream morphology. This was mainly due to continued rain, continued snow, and ice. And each of these is going to impact it in a different way. So the way weathering basically works is the key is it's increasing the surface area. So even though the volume that you are weathering is not changing, you are increasing the surface area exposed. And the more surface area you have, the greater weathering you have. So this is a positive feedback loop. As you break down, so if we have a square that's 4 square units, 2 by 2 by 2, and we break that down, we end up getting 8 cubes. Each of them have 6 sides. So if we do the math on that, we have 24 square units exposed on each side of the face. Now that we have 8 cubes, we have 48 square units. So we're increasing the surface area, and as we increase the surface area, we're going to break things down even more and more over time. So we have 2 ways of breaking things down. Mechanical, which is the physical breaking of rock into pieces, and chemical, which is breaking those chemical bonds that hold those molecules and minerals together. So think of it this way. If you start with a sheet of paper, mechanical is if you throw that into a shredder. It's still paper, but you're physically breaking it down by just shredding it and slicing it into strips. Chemical would be if you burn it. You cannot recover from that at all. You're fundamentally changing the chemistry of the makeup of that material. So mechanical weathering, we're not changing the composition, we're just physically breaking them apart. So there's a number of ways we can do that. It happens all the time in nature. We have a lot of different forces that are gonna take effect here. So we have hydraulic action, abrasion, which is just breaking them down physically. Frost wedging is a good one, thermal expansion, exfoliation, and biological factors. So let's take a look at these. So hydraulic action, anytime we're talking hydraulics, we're talking about fluids. So if we have water, think of those active coastlines that we talked about in coastal hazards, where we have those cliff faces that are just being broken down and broken down. That's all by hydraulic action. The waves are crashing into it over time, constantly, back and forth, back and forth. They're finding their ways into cracks and weak portions of the rock itself. Water is going to get anywhere that it can. So it's, like I said, the most powerful force on earth is water. Give it enough time and enough energy, it can do anything. So as it's increasing the pressure by crashing into it, it's going to decrease the pressure as it's taking away sediment. So as you're constantly making these changes in the internal pressure, increasing, decreasing, increasing, decreasing, you're going to keep weakening and weakening that rock until it starts to collapse. So we can see these everywhere, but specifically coastlines is a great example. Abrasion, that's where we have stuff wearing away, which is just like scouring or scraping using water, wind, anything that can just dig things away. So anywhere that we have waterfalls is a great example of abrasion. All that water is, if you're giving it enough of a gradient, enough gravity, it's going to fall onto a certain point. It's eventually going to break that apart just based on that constant abrasion. And you get deeper and deeper waterfalls driving backwards through the stream channel over geologic time. So something that helps with this, especially with stream channels, we have suspended load and bed load. All those little grains up from the headwaters, they're going to come in and it's acting like sandpaper, basically, or sandblasting is an even better example, because you're taking all of this grit in this fluid, smashing it into another rock. You're going to break it apart a lot easier if you have that kind of sediment material in it. So we see this in rivers a lot. We can see this at white clay. As we're weathering stuff away, it's going to chip away at whatever it can get to. These stream banks are just made of regular old soil, so it's really easy for the river to eat into that, and it just keeps carving and carving deeper and deeper until that river bank will just collapse. Frost wedging. I forgot to put it in here, but I had a great example of this in on my porch this morning. My sweet grandmother bought me this like crock that has our last name on it, and I put it out front and filled up with water with the rain, and I was like, oh, screw it, I'll take care of it later. So I go outside this morning and it is frozen over, and there is just a big ass crack on the side of it, and I'm sure she'll be just oh so pleased to see that when she comes to visit. But frost wedging is the process of anytime you have cracks in rocks fracture and break on their own certain cleavage planes. And you can see these everywhere. Water is going to trickle in there. Water can find its way into any conduit that it can. Gravity is going to do all the work for it, but water will find its way. As you get colder and colder temperatures, that water is going to freeze, and water is unique in that whenever it freezes, it goes from a liquid to a solid, it expands. So as you're filling it with ice, that ice is going to spread apart, increasing the internal pressure in those cracks and rocks. So you can get cracks that split outward. Also, if it can find a way underneath a block, you can get uplift in some cases. So that can help topple stuff over too. So you're gonna get this combination of all these different forces just breaking apart this rock just by freezing and thawing and then refreezing. Yeah, so ice takes up 9% more volume than liquid water. So if you have an ice cube and you melt it, chances are you're going to be left with less than what you think. We can also have thermal expansion. Whenever you heat things up, things tend to expand. That's true of all materials. So if you have, if you're an engineer and you're designing a large structure like a bridge that's going to be exposed to sunlight frequently throughout the year, you have to account for thermal expansion whenever you plan for that, because these things, even though it's a rigid structure, you have to account for some movement and some motion in anything that you build and design, because these materials will flex and they'll expand, especially with heat. Same thing can happen to your granite countertop. If you impact too much heat, it'll crack and create more cracks. If you create those fractures, you can get all sorts of stuff going in there. You're increasing the surface area, remember. You're going to increase the weathering amount. Exfoliation is really unique. It's a really cool process to study. It's a really cool and rare process to see happen in front of you. I couldn't find the video, but there's a video of just this whole rock face just popping up like a shotgun blast from this geology field trip, which is pretty cool. I'll try to find it and probably email it to you guys. So basically, all of these deep rocks, like this is a pluton, which means it's probably just this big piece of granite that was part of this magma chamber. It crystallized, the magma chamber lost its thermal energy, so we have a rock now. But there's all this confining pressure from all this stuff overlying it. So we're increasing the weight, we're increasing the pressure on the surface of that rock. So that rock is now used to that type of pressure, that amount of pressure. And it's solidified thinking, I'm going to stay at this pressure for the rest of my life. That's what it's thinking. Then once we get rid of all that overlying sediment, we get rid of all that stuff, all that internal pressure is still there. So because there's no weight supporting it and contrasting it, it's going to start breaking and expand. So it breaks up in these like sheets that just kind of fall to either side of the rock surface. These really long linear features that just kind of flake off, just like dry skin, basically. So as you have more uplift because you're releasing pressure, you're going to get more expansion and you're going to get more sheeting on the sides of the rock face. This has happened a few years ago at Half Dome Rock. If any of you are rock climbers, it's a really famous outdoor rock climbing area. It takes, I think, 3 or 4 days to get to the top of this. So you have to pack everything and be able to hang a hammock up there. It's kind of hard to see, but that red area, it's probably about 100 feet long. That was just a sheet of rock that exfoliated, fell off, and fell like a meat cleaver. So if you were caught in that, you're done. So it can be actually a really dangerous thing. Also, if you can imagine mining activities, you're basically doing the same thing. All that internal pressure, you're drilling right through it. So a problem with mining activities is that if they don't reinforce the rock properly, you get exfoliation in a confined space. That's going to be a lot more devastating. So all this exfoliation shoots off like a shotgun blast. So they have to be very careful and monitor how much is coming off the rock face, and if they can incorporate any external pressure to kind of keep that up as they're conducting mining activity. And we can also have biological activity. So tree roots are much like water, they'll find the path of least resistance. If you get a seedling that's in the cracks of a rock, it's going to get its root pattern to match the fractures in that rock. So as the tree continues to grow, gets more water in there, it's going to wedge its way, much like frost wedging, into the fracture of the rock until it splits it open. So you can see these all over the place. There are a couple in Pennsylvania that are really cool. We also have this picture down here. Remember when we talked about lichen and how we were able to date certain sediments from glaciers? This is one of those examples where lichen is going to introduce more photosynthetic activity onto the rock. It's going to absorb more heat. And if it can absorb more heat, you're going to have more thermal expansion. Okay, so all of that was mechanical weathering. Now we're moving into chemical weathering. So we're transforming the rock into one or more different compounds through different chemical processes. So we can do it through dissolution, hydrolysis, or oxidation. All of these require the universal solvent of water. So one of the best examples of chemical weathering is the Statue of Liberty. If you do not know, the original Statue of Liberty, when it was fresh, brand new from France, it was bronze. It was a nice bronze color. Most of that is from copper sheeting. And as you expose copper, if any of you have seen like corroded, if any of you work on your car, you probably see corroded copper wires, has this like green, greenish tint to it whenever it's corroded. Same thing basically happened to Lady Liberty for over a long period of time. So that's why it looks green now. So water, as I said, universal solvent. Number one, it's fluid. You can dissolve things in fluid. Number two, it's polar, meaning that it has an imbalance in its charges and it's chemically neutral. So that enables it to mix with a whole lot of things. So whenever we're talking about water's polarity, it means that its dipole charge is unevenly distributed. So we have excess negative charge on oxygen, and we have excess positive charge on hydrogen. Because we have 2 hydrogens per 1 oxygen, we have an excess of 1 positive charge in that direction. Because water always forms in that shape of the molecule, it's going to impact the way that it will bond with things in solution. So this is going to enable it to have, doesn't permanently bond with solutes and has very weak electronic interactions. So you can see how it's interacting with some sodium down here. Sodium has a positive charge. Chlorine, on the other hand, has a negative charge. It's changing the direction of that water molecule. So because of that, the dipole of that is going to, as water flows across the rock surface, it's going to basically pluck all of those molecules out and into suspension. So it's going to quickly bond with those and then unbond them. And there you have it. You have this dissolving. That's what dissolving is. Basically, you're just taking ions away and chipping away at it with water flowing over the surface. So this is what that looks like in person. So a long time ago, most headstones were made of limestone, especially in like early colonial America. Limestone was widely available on the East Coast. It's still widely available today. It's also a really important, has a very important use in early iron smelting. So if any of you go to central Pennsylvania, you'll probably find huge limestone boulder fields next to where they have these historical furnaces. You also see these weird pieces of like this almost glassy asteroid-like looking rock. That's called slag. That's a byproduct of this kind of smelting. But so if we have water splashed upon the rock, it's going to eventually dissolve that rock surface, plucking those ions out of the rock crystal itself. So for example, since we have limestone, limestone is another fancy rock of the mineral calcite, which is CaCO3. You add water and CO2, of which we have an abundance of in our atmosphere. H2O and CO2 make H2CO3, which is carbonic acid. You can also work that out to have calcium and bicarbonate. All that water that flows across the surface as rain or flood waters, what have you, if it's a river on a piece of limestone itself, it's going to wash all that away. So over geologic time, that's what we end up getting. So if you're ever out into the area of Kentucky, they have this little place called Mammoth Cave National Park. Mammoth Cave is one of the largest cave systems in the world. The problem with limestone caves, this creates a topography, what we geologists call karst. Karst is a Czechoslovakian word, I think. I think it's Czechoslovakian. Czechoslovakia has tons of these as well. They have an abundance of limestone. So a lot of early geologists went to study dissolution of rock. They went to Czechoslovakia. The Czechs got to name a lot of the features. So as you can imagine, like for sinkholes and caves, as you dissolve away that rock, you get instability from the top because you still have weight on top of that cave and you're eroding stuff on the bottom, you're going to get cave collapses. So the problem with most cave systems is that they're not very large just because they can't support themselves because they're literally cannibalizing themselves. As they're eating away at the rock surface, they're weakening it. So you're able to more preferentially collapse that cave system. The reason Mammoth Cave is so large and is able to grow so large is because there's a cap to it, where there's no more dissolution taking away from it. There's a cap of sandstone that's in this specific shape that takes all that weight away and distributes it evenly. So that's why the Mammoth Cave is so large. It has this basically buttress over it that allows it to distribute the weight, which is pretty cool. All right, hydrolysis. This is where we're looking at specifically silicates. Remember, silicates are one of the most common mineral groups that we have on Earth. Make up a very large portion of the Earth's crust. So here we have a piece of granite. Part of granite is potassium feldspar, the pink stuff that's in granite. Granite, you usually have quartz, that pink potassium feldspar, and some pyroxene and hornblende, those like black little specks. And sometimes you can get olivine, the little green stuff that gets in there. So next time you're picking out a countertop, now you know what to look for. So feldspar is, it's a clay mineral. So because of that, as you add water to it, it's going to break down into its dissolved SiO2, is the silicate tetrahedron, and kaolinite clay. So in areas that we have a lot of feldspar, once we introduce acid to it, we're going to break those bonds and you're going to be left with a pile of clay. And we have a lot of these in our area. I know the road I live on is Kaolinite Road because there is so much of this feldspar. The northern part of Delaware falls under that part of where the Canadian Shield came down. That's all granite. All of the toppled rocks and colluvium that come down from the sides of the mountains, they ended up in Delaware as well. So we have a lot of kaolinite from, as you can imagine, we're a low-lying state. We get all that water coming through. Hydrolysis is going to happen. We're going to dissolve and convert all that feldspar into clay. So this is an example in Providence Canyon, Georgia. They call it Georgia's Little Grand Canyon. None of that is really rock. All of that is clay. Huge, huge thick deposits of clay, like 150 feet deep. So this was basically created from a combination of the geological breakdown of feldspar into clay, and then the actual canyon was carved out from some poor farming practices. So they didn't irrigate properly, where all the drainage from this one field went into this gully. Because it's clay and because it's specifically kaolinite clay, it's really easy to wash it and weather it away. So you're left with these huge, huge canyon-like features in Georgia. So oxidation is another one. Oxidation is another way to describe rust. So if any of you drive a car from the 90s like I do, you're probably very familiar with rust and how problematic it is. Same thing can happen to a rock surface. Anytime you have rocks that have metallic minerals in them, like iron is the best one, you're exposing it to oxygen, and that's going to change its color. It's going to break it down, and the more you expose it to oxygen, the more likely it is going to break down. So most people are familiar with Ayers Rock in Australia. It's their biggest mountain. That's just one big piece of iron carbonate, basically. Huge, huge piece of iron. In this area, sometimes if you're lucky to find a rock formation, they have these like nodes that look like almost dinosaur eggs. These like rusty colored dinosaur eggs. They're really heavy, really dense. Those are called siderite concretions. Siderite is iron carbonate, FeCO3, and they literally are shaped like dinosaur eggs. Anytime my little cousins come over, I show them that. I'm like, oh, you got a dinosaur egg. Check that out, you little moron. They love it, go crazy for it. But oxidation is the same thing that happened to the Statue of Liberty. We're oxidizing all of that copper, getting that green color that we see today. So all of chemical weathering is still based on that Bowen's reaction series. So remember this looks a little different from what we had before, but remember when we were talking about different types of magma, mafic to rhyolitic, and the temperatures that they form at, that's going to define a lot of their chemical characteristics, as you can imagine. So we have our mafic rocks up here at the top. High temperatures, very, very high temperatures, 10 to 1200 degrees Celsius. That's when they crystallize. So that's their freezing point, basically. Think of it that way. So because they crystallize at such high temperatures, they need high temperatures to stay stable. So once they get up to the Earth's crust, they're a lot more unstable and they break down a lot easier. So as we move down Bowen's reaction series, we're getting into more and more stable rocks. They're the last minerals to crystallize. That means they prefer colder environments to crystallize at. So if we look at olivine, pyroxene, plagioclase, feldspar, these are pretty weak ones. They're pretty unstable. Remember, plagioclase is going to weather down into kaolite clay. It's really easy to do that. Olivine, you can barely ever find at the surface. Why is that? Because it breaks down the moment it gets to the surface. So that's why we can't find these rocks anywhere. And it's really, really rare to find them at the surface. One of our grad students, Quan Yu, he's an igneous petrologist. He studies deep mantle rocks. He actually was able to work with some samples that they took from seafloor drilling where they have these. They have to keep them in a specifically very, very hot, basically cylinder whenever they're not looking at it, because they'll just break down and break apart into this like greenish sand, which is pretty cool. They also have a field site in the Andes where they found some of these at the surface. So they're trying to preserve that site so they can keep looking at it, which is pretty cool. So yeah, so those are the mafic rocks. We don't see them at the surface all that often. And when they do come up to the surface, they tend to be more into basalts. So a lot more amphibole, a lot more other minerals breaking into it. But once we get to the lower temperatures, we have quartz, muscovite, K feldspar. This is the stuff that makes granite. You can go to Acadia National Park and all of their mountains are made of pure granite. All of the Appalachians are made of granite. The Rockies are made of granite. They're still here at the surface. They haven't broken down because they're so stable chemically. So that's how Bowen's reaction series plays into effect here. It's going to define the stability of the rock that we're looking at. So let's make sure you're paying attention. Of these five, which mineral is most susceptible to chemical weathering at Earth's surface? You can just shout it out. Do you know it?
Olivine.
Olivine. Why is that?
It's still
That's right. That's exactly right. So if olivine is at the top of that scale, quartz is all the way at the other end of that scale. Quartz quite literally will take over the world. It is incredibly, incredibly resistant rock. There's a reason that quartz countertops are becoming so popular. Not only do they look really pretty, they're also very, very resistant. Granite, if you're not familiar, you have to take really good care of it. So every so often you have to use a very special type of like oil to take care of it. That's because granite has a lot more of those unstable minerals in it. So if you're using your granite countertop and you're abusing it with like all your cooking shit, it's going to break down a lot more. Quartz, however, you can bang it with a hammer all day. You're not going to really have any problems. So quartz is incredibly resistant to mechanical. It's resistant to chemical weathering. All glass is made of quartz. Sand, once you fire it, turns into glass. That's why all your chemistry sets use glass. All of that is quartz. It's incredibly resistant to chemical weathering and chemicals in general. So because of this, it takes a lot to break it down, and it accumulates into large masses. That's why all of our beaches are covered in quartz. All of our vast, vast deserts, the Sahara, the Gobi, the Rub al Khali, all of these deserts are made of quartz sand. Okay, so let's talk about products of weathering. So we've broken the rock down. What do we get from it? So if you remember our sedimentary rocks lecture, we talked about grain size. So these are 4 different grain sizes that we have. We have gravel, greater than 2 millimeters, sand, 2 to 1/16 millimeters, silt, real fine stuff. You can't really see it with your naked eye, but if you grind it in your teeth, you can still feel it. And then clay, if you can't even feel any of the grains at all, not even if you chew on it. So which of these sediments is a soil, do you think? Feel free to take any guess. You think silt? Okay. Why is that? You know, that's a great way to find an answer. In this case, this was a trick question. So none of these are a soil. Why is that? All of these you could probably say are dirt in a manner of speaking, but it's not a soil. So a soil is a lot more than just the actual sediment itself. It's my hydrogeology professor, Dr. Helmke, told me soil is 3 feet between civilization and starvation. So that's why it's incredibly important. But soil itself is a complex ecosystem. It's a complex profile. It's a complex in everything. So we have 2 different examples here of a definition. Solid earth material that has been altered such that it can support rooted plant life, or any solid earth material that can be removed without blasting. One of those was a soil scientist. The other one was an engineer. So this is what is actually in soil. So as you can see, 50% of it is air and water, not even the sediment itself. 45% of it is the actual mineral particles, all that silt, the clay, the sand, all those small things. That's the actual mineral portion. And then we have 5% organic matter. So of that 5%, we have organisms like earthworms, insects, all the stuff that rides around in the dirt. We have the actual root stems of any plant matter. And then we have what's known as humus, not humus, humus in this case. Humus is the decaying stuff, all the dried leaves, grass, all the stuff that's actually dying and decaying in the soil. So that's going to be a really important portion of what defines a soil. So if you think about this, in a soil, 50% of that soil has to have pore spaces, at least. For there to be water and for there to be air, there has to be a pore space there. So a lot of soil is just empty space that gets filled up with water and air. So this is what a soil can be made of. Organic matter. We've got our silicate minerals that can get in there, some microbes that help break it down, our clays that we're breaking down through hydrolysis, and all of our oxides, our carbonates. So all of this weathering from chemical and mechanical means is going to break down, combine into a useful soil. So this is a soil texture diagram. We use 3 basic grain sizes to define a soil. Because as geologists and specifically soil scientists have a lot different nomenclature, but geologists, we care more about the mineral content. So we talk about the grain size because that's what we know. So the way this works is you have 3 axes, basically. Think of this as a graph. So you take a sample of whatever soil you want to study, and basically you put it under a microscope, you draw a line, you count every single grain that intersects that line. Of that total, you calculate the percentage of silt, percentage of sand, the percentage of clay, and you graph it that way. You triangulate until you find what kind of soil that you have based on this graph that we've created. When did we create this? I'm going to say, I think, no, 35, I think. 1935, I think was when we created this. Let's see, FDR, yeah, around 35, mid-30s. So this enables us to figure out if a soil is going to be good for agriculture, if it's good for building materials, if it can support a certain amount of weight, a number of things that we can learn from this. So you'll see in this middle portion right here, if anything falls in that area that says loam, we determine loam as a fertile soil of roughly equal parts sand, silt, clay, and some humus. So it's got a generous mixture of everything. It's really good for growing things in total. So if you go on the DCNR website for the federal government or the USDA, each of the states of the union has their own state soil. If you're really into that, you can read up on that. Some real dry reading, but each of these state soils is, in some cases, it's culturally significant. Most cases, it's agriculturally significant. So this is our state soil. Man, I have not woken up yet today. State soil. This is the Greenwich soil profile, which is a loam. So we have a bunch of different layers, and it may be hard to see with this image, but so this is from 0 to 4 feet. This is just a profile of just if they took a backhoe out into a farm field and just dug one big scoop, you can stand in it and take a look at the side of it. So we have a couple of key layers here. So we have a surface layer of brown loam. In the subsoil, we have an upper and lower brown loam. We get some more brown and then some yellowish. And then we get into the substratum, some yellowish brown. We get more sand down there, some loamy sand. So they're using these terms interchangeably as nouns and adjectives, which is great to confuse people. So here's where we're talking about pedogenesis, which is the actual formation of the soil. So unlike building a cathedral where you built from the ground up, here you're going to start from the top down. So everything pretty much starts with water. Water is going to be the energy and the transportation mechanism of all the things that are going to create a soil. So we have water percolation, which is just another fancy term for infiltration. It's going to enter all those pore spaces. It can enter faster if there's more biotic activity like worms, creating all these little channels that the water can flow into. So the rain's going to enter the ground. The trees are going to drop leaves. That's going to become part of the humus in the actual soil itself. All the microbes that are carried with that water are going to eat and decay that organic matter. We're going to metabolize that soil from that. And then all those ions that are created, remember water's polarity, it's going to carry that stuff down. It's going to pluck some stuff and it's going to percolate down further and further. And then we're going to get a zone of accumulation. So we have two key zones here. Zone of what's known as leaching. Think of the leeches that suck on your blood. We're taking stuff away from this zone, and we have a zone of accumulation. All that stuff we're taking out, we're depositing. So these things deposit in what we call as horizons. So remember our principles of geology, law of original horizontality. Because they deposit in horizontal layers, we just call them horizons. So each of these layers is going to be significantly unique, and we'll be able to define each layer based on its content, its chemical, both mechanical and physical content, and where it is in the profile. So we have 6 main layers that we see in each soil. Regardless of where we are on Earth, this is going to change. Like if you imagine a soil that if we take a backhoe out to the Sahara and we dig a 20-foot hole, we're probably not going to see some of these layers. We may see some surprising ones near the bottom, but we're not going to see some of the stuff up top. So we have an OAE BCR horizon. Each of these has its own nomenclature. So the O is going to be, think of organic. So this is all the dead stuff, all the biotic matter. A is going to be topsoil, what we describe as topsoil. Usually darker in color. It's got a lot of that decaying matter. That's where all the biotic activity, earthworms, insects, that's where they're going to be active. Then we have the eluviated horizon, which we'll define in a minute. The subsoil, which is the stuff below the eluviated horizon. Then we have parent material and bedrock. Now, most geologists include bedrock as a horizon because that's where all soil comes from. It's broken down sediment, so we think it should be in there. Most soil scientists won't even bother with that. It's not soil yet. It's just the rock. It's just the saprolite. But the parent material, that's where it's the actual weathered grains. So we're going to talk about each of these layers in a little more detail. Okay, so you have O and A. O is the organics only. A horizon, you have minerals and organics. So O horizon I describe as the stuff you rake. A horizon is the stuff you dig. So whenever you're planting something for your garden or so on, you want topsoil, where you want both of those. The O and the A horizon together is topsoil. You get all the benefits of decaying organisms, all that biotic matter, all that plant matter, all the stuff that has the nutrients in it. That gives you a really healthy soil for growing stuff in your garden. So now we're moving into the E horizon. E horizon is a zone of eluviation, not illuviation. Eluviation is the movement of materials brought into suspension or dissolved by water. So this is another fancy word for bleaching. So we're taking all of those ions, those enriched ions in this zone, and we're taking it out with that water. So water is going to flow through all the pore spaces, following gravity, path of least resistance, and it's plucking things out, plucking ions out due to its polarity, taking stuff with it. We're stripping those chemicals away. So because of this, the E horizon tends to be a lot lighter in color. If we're taking all those ions away, we're taking all of the like black organic matter, we're taking away any of the oxidized red minerals. So we get this like real pale color in the eluviated horizon. Then we get to the B horizon, which is just below that. That's the zone of accumulation. We've taken out all of those ions. We're starting to put them right where we want them. The B horizon usually has a lot of clays because clays are the finest grains. So they're going to get mixed up in suspension in that water flowing down through the soil profile. And we're also going to get all those ionic compounds. So we can define what kind of oxides we get at these horizons based on its color. So if we're at a red, we're oxygen rich. As you can imagine, more oxygen leads to more oxygenation, which means we get more rusting. So more oxygen rich, we get redder colors. Less iron oxides, less oxygen, we're going to get more yellow colors. Now we get to the sea horizon. This is what's called the youngest soil, meaning that it hasn't really properly formed yet. This is the weathered stuff, the stuff that's fresh from the parent material, that bedrock that's underlying all of this. So this is where we're getting new fresh soil. So this is more mineral grains rather than the other layers up top, which are more mineral grains, water, air, and all of our chemical compounds. So based on the number of horizons we can see, that's going to determine if we have a mature or immature soil. Basically meaning, is it a younger soil or is it an older, more refined soil that has all those layers? So which of these is the most accurate description of a soil? A, B, C, or D? C, that's exactly right. You've got air, minerals, water, and organic matter. You need all of that to make a soil. If we have just sand and silt, that's just parent material. That's just minerals. Silt, clay, and sand, that's still just parent materials. Air, water, and organic matter, that's just the shit you rake. So we need minerals, water, air, and organic matter to actually classify a soil. All right, so what affects soil formation? So obviously we have parent material, slope. We need time. We're working with geology. We're always going to need a lot of time to make these things happen. Climate is going to play a real key role. As you can imagine, soils are different in different areas of the earth. If you go to the Gobi Desert, you're going to get a different soil than if you go to Newark, Delaware. And then the biome itself, animals and vegetation is going to play a really, really key role too. So we call it parent material because that's where the soil comes from. This is the bedrock, the residual soils, all of this is formed in situ, meaning in place. So soils always form in situ. If it's transported, it's sediment. If it forms in place, it's soil. So all that unconsolidated material can also form through transport. So remember we have, remember those images that we had with all of that airborne dust that's coming up from the Sahara? We can have that form its own soils if it finds a place to rest and deposit. So that's considered parent material. It's parent material from another continent, which is pretty interesting. But if it's easily erodible and it's able to be transported long distances, but it finds a place to deposit, that's where we're going to get the beginnings of that soil. The slope is going to play a key role here too. As you can imagine, steep slopes, we don't have enough real thick layers of soil. Things fall with gravity over time and soils take a long time to form. So if you keep falling off of a slope, you're not going to form a real stable soil. So they're unable to rest and develop, and slope in soils is going to be really important when we talk about mass wasting in the next few days. Now, shallower slope, think of floodplains, where we have that real gentle gradient where we can develop all those river meanders, all those thick deposits of flood material. This is where we can get our thickest layers of soil. We get our most amount of organic matter. As you can imagine, we have really sparse organics on steep slopes, just because all the vegetation also has to adapt to that slope. So if we can reduce the slope, we're going to impact and increase our deposits of soil. Time. So soil, as we said, develops from the top down. So the longer time that we have, the more development that we'll get. So right here on the left, we have disintegrating rock. So that's just if you expose that brand new fresh rock surface at the surface, taking away all the stuff overlying it, and now you're exposing it to the elements. You're gonna bring in rain, you're gonna have sheet wash over it, you're gonna abrade it, you're gonna get hydraulic action, frost wedging. Maybe if you're lucky, you can get some root wedging in there that'll break things apart. We're gonna continue to break up this bedrock until we get parent material. So that's all the mineral content. We're breaking it down into grains of sand, silt, and clay. So all that real small stuff. We'll start to develop some of the organic matter on top, real sparse at first, but then as time goes on, we're going to develop more and more of it. So then we'll develop an A horizon, the parent material horizon of the C horizon. And then as we keep building up, we're going to eventually get to the point where we can start leaching out some of those ions, and we'll get a good quality B horizon. So these take a long time to develop. So whenever we have a mature soil profile, we can have distinct visible layers. There's a clear structure to it. It's deposited in a continuous horizontal line. So we can actually map these out, map their distribution, and we can learn a lot about the overall weathering processes and erosion processes in a given area just from the soil. Whenever people say older than dirt, that isn't just a saying for the hell of it. Soil is super old. Because it comes from bedrock, think of how old rocks are and think of how long it takes to form rocks. It takes even longer to form a soil. We have to break down the soil, the rock first, just to even get the grains. And then you have to develop everything on top of that. So it takes a long time, 40 to 100,000 years. Out of the three of these, which seems to be the most mature profile? A, B, or C? Yeah. C. What makes you say that? Yep, easily visible. That's the key. So this is taken from a paper that was looking at and comparing different types of soil profiles. Something that we can notice is we only have an A and a B horizon, A, B, and C, and then we have like 8 horizons here. So we've got a very well developed soil over there on the right. Alrighty. Okay, let's talk about climate. So we've mentioned climate change in the past. So changing climate will also impact your soil. Differences in climate will impact the way your soil works. So if we have hot, humid climates, we're going to generate soil faster. You get more rain, so more water means more chemical weathering. Remember, water is the universal solvent. It's going to drive all those chemical processes. We get higher temperatures, we're going to get more weathering because we'll have a lot more thermal expansion. Higher temperatures bring in all sorts of other weathering factors. So higher temperatures, we get a lot more soil development. So this is just comparing 2 different areas. We have North Vietnam, more tropical, closer to the equator. We have the Alps and the Dolomites. Both of these have the same rock material underneath them, limestone, but they have incredibly different soil profiles. So you don't see a lot of farms up in the Alps. You see cottages and ski resorts. But in North Vietnam, you're going to have a lot better developed soil, so that you can get a lot more agriculture going in those areas. As you can see, they're doing terrace steps into the side of the mountain to increase the surface area that they can grow on. So I know this is a terrible image in terms of quality, but this is what we're looking at when it comes to climate. So all this stuff at the bottom is the types of soils and thicknesses that we can get from different climates. So we have the tundra over here on the left, and we're just going to increase in temperature on the right. Something we're going to change is the amount of precipitation that we get. Maybe we're getting a little more precipitation than other places. So you can see the tundra, we're really dry and we're really cold. So we're not going to develop very many soils there, not in thick deposits. In the podzol zone, that's where we're a little more temperate. Think humid northeast of America, that's a good example. Then we're getting into the steppes and the semi-arid deserts. We're going to decrease because we're decreasing in temperature again. We're also decreasing the amount of precipitation. So more drought, we don't have any of those driving factors impacting the weathering processes. Then we get to tropical forests and boom, we're going to develop so much soil just because we've got everything. We've got temperature, we've got precipitation, we've got vegetation, everything working in tandem to develop a really thick deposit of soil. Then once we get down into the savanna, we're getting less and less. So each of these, take a look at the legend. We have fresh rock at the bottom. Then we have that chemical weathering zone, the clays, and oxides and iron oxides. So of those, which one is most like Delaware? A, B, C, or D? You can just shout it out if you know it. Probably the Podzol zone? That's right. So we have a pretty temperate climate, not very high temperatures, but we get enough precipitation that we can support a decently thick layer of soil. So even in coastal Delaware, we're able to develop this pretty well. So we have so many different types of soil to define and look at. And we're not going to look at all of these. We may look at some examples, but this is a small list compared to the actual number of soil types. Soil scientists just go nuts about classifying different types of soil. So, but you can see that there's a wide distribution of them, and they seem to be aggregated around certain areas. So if we look at, let's see, pick one anyway, gelisols. So we have gelisols in that light blue. Where do we see the light blue? All up in Siberia, in Svalbard, up in northern Canada, northern Alaska. So what do you think the soils are like up there? There a lot of water moving around there? No, we're in permafrost areas up there, my dude. Huge areas of permafrost. So we're not getting probably not getting a lot of water moving around, but there's enough there already that there is some type of soil. Some things can grow in it. Really hardy stuff, really sturdy vegetation can grow in it, but very rare. How about spodosols, that light purple? We see that in like Maine area, southern Canada, Scandinavia, Kamchatka Peninsula, northern Scotland. What kind of trees are in those areas? Are we dealing with oak trees or more like pines and spruces, evergreens? So evergreens create really unique soils. Whenever you dig up around an evergreen, they come up like with this like thick green color. They're incredibly acidic, and only evergreens can really grow in that kind of acidic soil. And that's from all the pine needles that come out of the tree itself, deposit in that O horizon. So you get all these weird things. So each of these is going to be geographically located. So whenever we're studying soils, we're studying pedology. Ped meaning the root word is, I think, Latin for foot. So it's just the stuff under your feet. Real unique name. So whenever we're talking about building things, whenever we're trying to construct residences, build roads, highways, we have to think about the soil types and the soil properties that go into it. If you're building on a certain type of soil that weathers readily, be prepared to replace shit on it all the time. So better planning, better consideration of the soil type itself, and better understanding of it can help you prepare for mitigation or adapting to those weathering characteristics. So certain soils are what's known as expandable soils. So whenever they absorb water, they're going to expand rapidly and they can swell. So if you have something built on top of an expandable soil, you can have a lot of structural damage. You can have tipping in your house. It can ruin your floorboards, stuff like that. If any of you are familiar with Wyoming, Wyoming is home to something known as Wyoming bentonite, and bentonite is probably the worst when it comes to swelling clays. And they used to sell land, just acres and acres of land in Wyoming for cheap, dirt cheap, but like pennies on the acre. The reason for that is the moment you drive out there in the rain, you'll get your vehicle stuck to the axle in this clay. The moment it just swells up and it can swallow any car. And then afterwards it dries and then it's almost as hard as concrete. So then you're not getting it back out at all. So tons of people bought land out there, and instead of being able to build houses on it, they ended up mining bentonite clay. Bentonite clay is actually sometimes useful too. It's sometimes useful to have something that expands. If you're drilling a well, be it a water well or a natural gas well, the side of that borehole, you have to plug it up with something. If you have something that you can just pour down dry, pour in a little water, and it expands, it's going to create a perfect seal around that. So I used to use bentonite all the time whenever I was working in environmental consulting, drilling wells. So we would throw bentonite in the borehole of the well, seals everything up on the outside, so we see what's actually going on in the actual groundwater. Nothing's leaking through the sides. But if you have swelling clay under your house, you're going to have problems. So as you can imagine, all different types of soil is going to swell and shrink. So you'll get these constant motions of swelling and shrinking. If it happens uniformly underneath your entire house, you'll get subsidence of your house. If it happens on one side, you get leaning, or if it's a little differential, you can get cracks in your foundation or your house itself. So if we look at expanding soils, these are the ones in pink. So we've got a bunch up in the Dakotas, Montana, Midwest, lines of it in Texas, Louisiana, lines of it in Mississippi. So why do we have so many expandable clays in Louisiana? Yeah. The amount of rainfall? Kind of. What's the big waterway that ends up in Louisiana? The Mississippi. All of that stuff carried in suspension, it's got a deposit somewhere. Bottom of Louisiana is the mouth of the Mississippi River. You're depositing all those clays. So over time, it's just built up all of these expanding clays. That's created a big problem in the area. Because there's a lot of good farmland in there too, but expanding clays make it a real hassle. So now we get to the hazards portion. Is soil erosion a natural hazard? Short answer, yeah, it is. It can create a big problem. So soil erosion is the grain by grain removal of that mineral and organic matter. Remember, soil is both of those, all of that. So if we take wind and water, we're gonna erode that away. So right here in this picture, this is what's known as a gully. This is formed just from runoff, overland flow. This is how we start creating stream channels. So the earliest stream channels started as just little gullies, and they grew and grew and grew. Remember, weathering is a positive feedback loop. We're increasing more surface area, we're going to increase the rate of weathering. So it's a very rapid and exponential process. So keep in mind, we're still working with budgets here. So if we're eroding a soil, but we're also accumulating soil, and we're doing that at the same rate, there's no net change. So it's not really a hazard. But if we're exceeding the rate of formation with the rate of erosion, that's where we're starting to get into the hazard. So this is from a freshly plowed field. I don't remember where this picture was taken. But immediately after plowing the field, turning over all the soil, huge precipitation event. Because you don't have any of that root matter, you don't have anything locking that soil down, it's just going to wash everything through, wash everything away, and soil is going to find the best and least path of least resistance. So that's where you get these huge gullies. So it's impossible to stop. You can't mitigate it at all. That'd be like trying to stop the rain, and we can't do that. So good luck. So this is something that we're going to continue to deal with. The only way we can really mitigate with it is try to monitor gully formation and then kind of reroute water away from it. But then you're digging trenches in certain areas. So we're good at pushing things away. We're not always good at figuring out where they're going to end up. So that's another problem that we have with gullies. So we get a lot of gullies all the way down here in southern part of the United States. All of that is part of the coastal plain. Remember, coastal plain area, we're getting these real thick deposits of soil, very low slope, very low gradient. So we're gonna be able to just carve through all this soil if we have enough rain. So most of that is formed by water, but we can also get it from wind. So this is in Utah. That top picture was taken maybe 6 hours before the bottom picture. You can barely see, I think, is that Monuments National Park? I'm not sure. It looks kind of like it. Doesn't look red enough, but it's in the same general area. So we can accelerate soil erosion in a number of ways. So around the time of the Great Depression, you've probably heard of what's known as the Dust Bowl. Center of America is America's breadbasket, grows a lot of wheat, a lot of corn, huge agricultural area. It still is today. Back in the 30s, we did not have a U.S. Soil Service, which we still do to this day. So that was actually part of FDR's whole New Deal whenever he was trying to revamp the U.S. economy after the Depression. Part of it had to do with establishing better farming practices to create sustainable soil. So the problem with this area is that at the same time that we were using all these poor farming practices, we also had an incredible drought. And that drought accelerated the different types of practices that we had to use. So we were leaching out so much stuff from the soil. All that dry air is going to kill all of our vegetation. Nothing's locking down the soil. All that root growth is going to help us keep the soil locked in. Then you have all these sweeping winds that are going to carry all of that dust everywhere. So you get dust that accumulates by the foot in the 30s, which is pretty crazy. You're digging out dust every morning. You got to like cover everything before you go to bed. Crazy time. Since then, the U.S. Soil Conservancy has taken upon itself to like enact and advise agricultural practices. So we've gotten a lot better. We don't have huge dust storms in these agricultural areas anymore. You'll still see it in like Monuments National Park, but you can't really do anything about that. But our agricultural practices have gotten a lot better and we're able to mitigate against that. We can also accelerate these by deforestation and including poor farming practices. So Haiti has a big flooding problem. It's an island nation. It gets a lot of precipitation, a lot of rain throughout the year. So it gets a lot of flash floods. Anytime you get flash floods, you're going to carve stuff out. It's a lot of water moving really fast. in a short amount of time, you're going to start carving and eroding soil away. In addition to farming practices that are usually built around deforestation, so they're cutting down more trees to make room for more farmland. So that's going to influence more and more soil erosion. So in Haiti specifically, around 15,000 acres of topsoil are eroded each year. So they have to replace that each year. That's a ton of soil. But you need it because you got to grow stuff because you got to eat, right? So it becomes a very, very expensive process. As well as like all of this soil ends up somewhere. So sometimes it clogs up waterways. You can end up with fish kills if you have too much sediment in a river system. So it becomes a problem. You can also have what's going on in Iceland, deforestation combined with overgrazing. So Iceland is it's a very beautiful country, but they do have a lot of urbanization on Iceland. It's a growing population. They got to build around that. So they're deforesting a lot. Also, before the modern times, whenever the Vikings discovered Iceland, they brought over sheep. And sheep like to eat anything that isn't nailed down. So if you have a population of sheep with not a lot of natural predators, that population of sheep is going to grow rapidly, and it's going to eat everything in its path. So overgrazing, where you're eating all of that grass, keep in mind, while grass is only this tall, its root systems are probably 2 times as tall as I am. Huge root systems. These can lock up so much soil with their intertwined root systems. So if you kill all of that by overgrazing, you're going to end up eroding a lot of your soil. So you get these like weird gullies that you see in that top picture there. Okay, and then of course, as with everything, humans ourselves, we are a geologic factor. We are a geologic force on this planet. We've done a lot of mining, blasting, agriculture, anything you can think of. We've dug stuff around on the earth. So we're doing a lot of erosion because of all of our development. A third of the world's cropland topsoils are eroding too fast. And as we've discussed, it takes a long time to develop a proper mature soil. So that's why the U.S. Soil Conservancy, similar conservancies around the world care about conserving soil and best farming and agricultural practices so much, just because once they're gone, it takes a lot of work to create something that would be able to replace it. I'll say it again, it's 3 feet between civilization and starvation. One of the most important things you can study, and you walk over it all the time. Yeah, same as what we said here. It takes 1,000 years to form 50 millimeters of soil, 2 inches of soil. And you need a lot more than that to grow corn or wheat or anything that tastes good. You need a lot more of that. It needs a huge horizon to soak up nutrients, to soak up water. So you need a lot more of that. So what ends up happening? We talked about this with some of the other examples. Agriculture is a lot less productive because if you have less arable land, the soil profile is not very healthy. So you're going to end up relying more and more on gene editing and preferential selective breeding of like different crop yields. So you end up relying on it too much. You have food shortages, of course. If you can't grow shit, you're going to have a famine that creates huge human crises. We mentioned soil washing into waterways. Too much sediment yield is going to destroy certain ecosystems. So not only are you impacting your land-based agriculture, you could also be impacting your fishing industry. Where else are you going to get your food? And then, of course, we have increased flooding. So if we erode so much, we're creating these channels, these conduits for stuff to flow. We're going to increase the flooding risk in the area. So we got a lot of things all working in tandem. So how do we mitigate against this? So there are a couple of different ways that some farmers have figured it out. Contour plowing, where instead of just making straight lines, which we are so fond of doing, the best example of the change in city engineering is that I can think of is look at the aerial map of Boston and then look at the aerial map of New York. And you'll see a change from all of these weird circles in Boston based on the colonial times to New York, which is a grid system. So we've implemented that grid system into everything just because straight lines are the easiest. So instead of making that grid system whenever you're plowing, if you plow with the contour of the elevation of whatever hill you're on, if you're matching the topography, you're going to drastically decrease erosion. The water will behave more like it's in its natural state. So while this may take a little more time, a little bit more energy, it may save you a lot more money and a lot more time in the long run, because you won't be trucking in new soil, you won't be dealing with flooding damage, you'll protect your crop yield a lot more. If you have a lot of flooding, it's going to ruin your crop yield. Something that's been going on in France for a very, very long time is hedgerows. So you'll see these anytime you go over to Europe. They're very fond of hedgerows over there. Created a lot of problems for the Americans in World War II when we were going into Germany. They're really hard to cross, but if a tank can barely get across it, water is probably going to have problems too. So if you build up all these hedgerows, it catches wind, prevents wind from scouring out any of the freshly tilled soil that you're digging. It also helps to separate and create conduits for water. So along each of those hedgerows is a ditch, a drainage ditch that any excess irrigation can just drain right out, and you can control the rate of infiltration. Those can flow into retention ponds too. So a lot of really simple, really elegant solutions to these problems. Another one, and really easy one, crop rotation. If you have the same type of crop year after year after year, you're going to increase the stress on that soil. You're going to decrease the nutrient yield from that soil. But if you rotate your crops and you are able to create a budget of those balanced out areas, you can create a better soil horizon. So if you grow stuff that's clearly meant to just live there for a bit, by the winter it dies, all that decaying organisms enter into the O horizon, the A horizon. That's going to rejuvenate that soil. So that's another really easy mitigation strategy. So while soil erosion is still a problem today, we've drastically approached this as a huge issue, and we've made some really great strides, really simple strides into addressing this. That is all I have for soil. Anybody have any lingering questions? No? All right. Nobody just wants to chat about soil? I don't blame you. That's why I study rocks. Keep in mind, keep an eye on Canvas. You'll have until the end of the week to get anything in that you haven't done yet. After that, donezo. So keep that in mind. Keep studying for your exam 3. You did great on exam 2, so keep that momentum. At this rate, I was not really expecting to get that done. So like we may be able to have a good review session before the exam too. So stay tuned. Have a great Monday, y'all.
Thank you.
Thanks. Have a good one.